Welcome to our talk on our paper, Bodily Behaviors in Social Interaction, Novel Annotations and State-of-the-Art Evaluation. I'm Philipp Muller from the DFKI in Germany, and this is joint work with colleagues from INRIA in France. I will start and Michael from INRIA will take over in the second half of the presentation. Bodily behaviors are central to social interactions, and they convey a lot of important information about the involved individuals, as well as about the relations between interactants. For example, displacement behaviors like grooming, face touching, or fumbling are related to stress regulation. Self-touching and gesturing is related to leadership, and open posture is connected to attraction. These are just some examples, and many more links between bodily behaviors and important attributes of interactions exist. In contrast to their importance, automatic detection of bodily behaviors from video is not well explored. This is to a large extent due to the lack of suitable datasets. In our work, we present the first set of publicly available annotations of bodily behaviors embedded in continuous group discussions. Both human annotation and automatic detection of bodily behaviors are challenging. Bodily behaviors can be extremely subtle. The example of fumbling on the left requires a very fine-grained analysis of finger motion. Fumbling can also be difficult to distinguish from, for example, scratching, which is shown in the middle. On the right is an example of grooming, for example, which means moving the fingers through the hair in a combing movement. Apart from being challenging to detect on their own, bodily behaviors are often interleaved or even overlapping. The left shows gesticulating within fumbling behavior, and the middle shows face touching while the arms are crossed. On the right we can observe gesticulating, shrugging, crossed legs and fumbling. At least fumbling, shrugging and crossed legs occur at the same time. To enable progress on the challenging problem of bodily behavior detection, we collected a novel set of annotations. As a basis, we use the MPII group interaction dataset. This dataset consists of groups of 3 to 4 participants discussing on a controversial topic for 20 minutes each. In total, 22 interactions of 78 participants were recorded, resulting in 26 hours of human behavior. The participants were recorded from several viewing angles with frame-synchronized cameras. This dataset has been richly annotated with various phenomena and is also used for the grand challenge Multimediate, held at ACM Multimedia this year. Tasks of the challenge include back-channel detection and agreement estimation, as well as eye contact detection and next speaker prediction. By adding bodily behaviors to the set of annotations available on MPII group interaction, we create new possibilities for multimodal behavior analysis and prediction. The set of bodily behaviors we choose for annotation was inspired by the ethological coding system for interviews introduced by Troisi in 1999. In our work, we focus on behaviors of the ethological coding system that involve the limbs or the torso as opposed to just the head. While behaviors like smiling or nodding can already be reliably detected, behaviors like fumbling or grooming still pose a large challenge. In total, we annotated 15 behavior classes on the full MPII group interaction dataset. Annotation of bodily behaviors is both very time-consuming as well as to a certain extent subjective. To strike a balance between reliability and effort, we opted for a two-step annotation procedure. In the first step, one annotator completely labeled a video. In the second step, a different annotator reviewed and corrected the annotations of the first annotator. This plot shows the class distribution of collected annotations both in terms of the number of frames that were annotated, as well as the number of annotated instances. An annotation instance is defined by the beginning and end of a behavior. For both measures, we observe a highly unbalanced class distribution. When looking at the frame numbers, the number of frames, crossed legs are annotated for almost 1.5 million frames, and other classes only for a few thousand frames. On the other hand, when looking at the number of instances per class, legs crossed is among the least frequent classes. This is due to the fact that crossed legs are a static posture, which is kept for relatively long time periods. Gesturing, on the other hand, is often started and stopped to underline different aspects of speech. The large class imbalance of bodily behavior represents a key challenge for prediction approaches. Earlier, we already discussed that bodily behaviors might co-occur. This plot quantifies the extent of class co-occurrences in our annotations. Each row represents a behavior we are looking at, and each column represents a behavior that co-occurs with the first behavior. For example, let's focus on the third to last row, the shrug. In 20% of shrugs, there's also a gesturing with the hands. This makes intuitive sense, as both shrugging and gesturing are frequently used to underline what a person says. We also observed that legs crossed often co-occurs with shrugging. In fact, legs crossed co-occur strongly with most other categories. The main exceptions are stretching and settling, which also tend to involve the legs. To estimate the quality of our annotations, we conducted a dedicated study to test the agreement of our annotators. 3 annotators independently rated 4-second-long clips sampled from the dataset. In line with previous work, we computed the agreement of 2 annotators by dividing twice the number of annotated behaviors for which they agree by the total number of behaviors annotated by both. The plot shows the averages of these agreement scores per class. All behaviors except lean towards reach an agreement of above 0.5. Legs crossed, fold arms, and gesturing reach the highest agreements in the range of 0.8 to 0.9. We decided to include all classes in our evaluations. Based on the concrete use of the dataset, future research might consider to do the same or exclude classes that reach comparably low agreement. With this, I hand over to my colleague Michael.
Hi, I am Michael from INRIA, and I will present an evaluation of the state-of-the-art methods that serve as baselines to compare against when developing more advanced methods. We took 4 existing feature extractors, I3D, Temporal Segment Networks TSM, Temporal Shift Module TSM, and Swing Transformers. The first experiment was to evaluate the feature extractors in classification setting, that is, a setting in which we predict 1 or more action labels given a short video clip. That contrasts with the detection setting, in which we are given a long video and need to predict the action labels together with their beginnings and ends. So for this classification setting, we need to somehow partition the dataset in the short clips. Depending on how many labels we associated with a single video clip, we consider 2 labeling settings, single label and multi-label. In the single label setting, the dataset is split into clips of 1 label but various length. It can happen that 1 frame is a part of none or multiple video clips. On the other hand, the multi-label setting splits the dataset into equally long clips containing all annotated labels. Each video frame appears exactly in 1 clip. We evaluated the mean average precision of all mentioned feature extractors. To illustrate the complexity of the problem, we also include the random classifier. Mean average precision is evaluated in both micro-averaging and macro-averaging. Micro means that the same weight is shared across all samples, while in macro-averaging the same weight is shared across all action classes. The best result is reported by the Swing transformer in the multi-label setting. We also tried 2 modifications in the evaluation procedure. First is excluding 2 static classes, legs crossed and fold arms, and second is class balancing by randomly selecting 20,000 samples in each class. Systematic advantage have excluding static classes for single label setting, including static classes for multi-label setting, and using no class balancing. Swing transformer as the highest result method is further analyzed for class confusion. For example, in the single label setting, groom is predicted very well, but many classes get confused as fumble. As expected in the multi-label setting, the legs crossed class is causing confusion because it often co-occurs with many other classes. Now, for action detection, we use the Pyramid Dilated Attention Network (PDAN) introduced by our colleagues at INRIA. In addition to mean average precision, action detection is evaluated also on the F1 score and using micro and macro averaging as well. Best results are reported for the PDAN model with input features extracted by the Swin transformer. This figure illustrates detection predictions on 4 independent frames. The first frame has 4 true positives: fold arms, fumble, leg movement, legs crossed. The second frame has correctly detected lean towards, but also falsely alarmed adjusting clothing and settle. The remaining 2 frames show false positives of smearing hands and groom, while misdetecting adjusting clothing, scratch, and legs crossed. In conclusion, we extended the spectrum of annotations on the 26-hour-long MPII group interaction dataset with 15 new behavior classes. The dataset and annotations are publicly available. We also provide an evaluation of PDAN action detector using 4 state-of-the-art feature extractors that serves as a baseline for further evaluations of new models. Dataset is available for download at this link. Philip and I thank you for your attention, and we invite you to a deeper discussion at our poster number 2821.